Hi guys, today we are going to discuss about the diodes. Diodes are the electronic devices that allow the passage of current in only one direction. We know that the diode consists of P and N type of junction. It has two regions, the P type and the N type. When it is forward biased, it allows the current to pass, and when it is reverse biased, otherwise it will not allow the current to pass. So they have two electrical connections, the anode and the cathode. As I have mentioned earlier, that the P type and the N type. The P type is called the anode, and the cathode is the N type. About these anode and cathode we will discuss later. The electron flow from the cathode to the anode. As we when we discuss about the electronic flow, that it will always be about from the cathode to the anode, from the N type to the P type. Otherwise, if we discuss the mention the conventional current, that will definitely will be from the anode to the cathode. So we have to keep in mind this thing, that either we are discussing about the electronic flow or the conventional flow. So the two types of diodes, the thermionic poles and the semiconductors. Uh, and our concern will be about the semiconductor devices. We will not discuss about the thermionic walls. So, gentlemen, you know that the semiconductor devices have created the revolution in the electronic industry. So we will discuss about these semiconductor devices in this lecture. First of all, the basic, the semiconductor element, that is the silicon or germanium. These both are used much more. So we'll discuss the let's see the construction of the silicon atom element. Here is the nucleus of element containing the proton and the neutrons. The atomic number of silicon is 14. So to complete its valence shell, it has the tendency of 4 electron to accept. So you can see that the black color, these are the electrons, and the holes, these are the empty spaces to accept the electrons. All the semiconductors have the 4 electrons in their outer shell. So to accept to complete their valence shell, they need more 4 electrons. So this is very important property of the semiconductors, which will be used for all semiconductor devices. Let's see that this is the lattice of silicon, how the silicon element atoms exist in the normal life, that they make covalent bonds with each other and exist in the form of a lattice. This is the very important property of the silicon element, that these atoms exist in the form of lattices. These are crystals. So as we know that these have 4 electrons in their valence shell. So they every atom will need 4 electrons. So they make covalent bonds with each other by sharing 4 electrons each. They have in the bond of 2 atoms. They each have the electron share of 4 electrons to make a covalent bond. So as you can see that each atom now has a full outer shell after making the covalent bonds. And we'll discuss the very important aspect of the semiconductor devices, that is the doping. We dope the semiconductors to improve their conductivity. It is very important property. So we'll discuss about it, that what is doping and what are the types of doping, and what is the importance of the doping. The doping is the impurities are of two types. First one is the donor impurities and the acceptor impurities. Gentlemen, the name indicates the donor impurities. It will definitely will give something. Will have the tendency to give something, and the acceptor impurities will have the tendency to accept something. Here, in this case, the donors are the givers of the electrons, and the acceptors are the tendency have the tendency to accept the electrons. First, we discuss about the donor impurity. What is donor impurity? An impurity element is added which donates excess electrons. Gentlemen, when as we have discussed before, that silicon has 4 electrons in its outermost shell. So if we add an element of group 5 which have 5 electrons in its outer shell, so when the group 5 element will make a covalent bond with the silicon which have the 4 electrons in its valence shell. So 4 electrons will bonded with the 4 electrons from the impurity, and 1 electron will be remaining, which will act as the free electron, and will cause the electronic current to flow. The donor impurity group of elements have 5 valence electrons, and the elements in the group 5 are the phosphorus, antimony, arsenic, etc. And these are called the negative or n-type semiconductors. Why these are called n-type semiconductors or negative semiconductors? Because when I have mentioned that these have 5 valence electrons, after making covalent bonds with the silicon or germanium atoms, the 4 electrons will be bonded with the 4 electrons of the silicon. 1 will be remaining free, so this will be a free electron. So all the material will be called as n-type semiconductor or negative due to having free electron. Gentlemen, here a point to be noted, that all the after doping the material, the overall material will not be negatively charged. Then, as we have mentioned here, this is n-type semiconductor. It doesn't mean that it has a negative charge as a whole on it. It will be a neutral material. So the cost to call them as the n-type semiconductor is only the reason we call them the n-type material is the existence of free electrons in them. We can see here the n-type semiconductor crystal. We will see after doping what changes will be occur in here. After doping, we can see that free electrons are here. These are the free electrons in it after doping. Gentlemen, you can see that these are free electrons I have mentioned earlier. Next, we can see that this is the antimony atom, which have the atomic number of 51, and it have 5 electrons in its outer shell. So it can be used as the donor impurity. And here, when these are the 4 atoms of silicon, when it makes covalent bonds with the silicon atoms, the antimony, after making the 4 electrons will be bonded with the silicon atoms, and 1 electron will be remaining, which will be used after doping as a free electron. You can see here, this is the free electron, and it will be after doping with the antimony atom, the material will become the n-type material. And next comes the acceptor impurities. What are the acceptor impurities? As the name indicates, these accepts the electron. These have the tendency to accept the electrons. An impurity element is added which has only 3 valence electrons, one less than required to make the interatomic crystal. As we have mentioned that to make an interatomic crystal, to complete the lattice, the silicon or germanium element atoms have they need 4 electrons to complete their outer shells. So when we dope them with the element which have 3 valence electrons, so the 3 electrons will be bonded with the 3 from out of 4 electrons, and will be one empty space will be created here to accept or to we can say that it will be a free space to accept the electron. The acceptor impurity elements include, these are also called the group 3 elements, have the gallium, indium, boron. Such impurities are known as acceptor impurities as they accept electrons from neighboring atoms. The deficiencies in the valence bond are holes and appear as positive charges. The holes is a very important term used in the acceptor impurities, and this is called a positive or p-type semiconductor. Again, I remind you that the positive or p-type semiconductor doesn't mean that it have a positive charge on a p-type material. Always the p-type material will be as the neutral material. Only the p-type property indicates that it has holes in it to accept electrons. Again, we can see the p-type semiconductor crystal after the doping of the p-type semiconductor material. It will create the free electrons, free holes to accept the electrons. You can see here the boron atom, which has the atomic number of 5. After distribution of electrons in the shells, you can see that the outermost shell of boron have 3 electrons, and after the combination with the silicon atoms, after the doping of silicon with boron, the structure you can see here that the 3 boron electrons will be bonded with the silicons, and one free space will be available to accommodate the electrons. And after the doping with boron, the semiconductor material will become as the p-type or positive semiconductor. Here come the terms the majority and minority carriers. When we discuss we talk about the n-type semiconductors, the majority carriers will be the electrons, and the minority carriers will be the holes. Why we call these the majority carriers? The electrons here are majority carriers because the major current or major function will be carried out by these electrons. So these are called the majority carriers, and the holes will be play their role as the minority carriers. These will create the current, a very minor current to flow. This will and that current will be also called as the leakage current. And when we discuss talk the p-type material, the majority carrier will be the holes, and the minority carrier would be the electrons. As the major role played by the would be played by the holes, and the leakage or minor current will be created by these electrons. So these will be called as minority carriers. So, as a summary, we can see that the n-type semiconductor electrons produce a large forward current called the majority carriers, and a small reverse current is also produced due to the movement of holes in the material, and this is the minority carriers or leakage current. And when we in contrast discuss about the p-type semiconductors, the holes produce a large forward current called the majority carriers, and the electrons produce a small reverse current that and are called as minority carriers or cause the leakage current. Gentlemen, now our discussion of introduction of diodes has been completed, and next very important the PN junction, its construction, and the operation of the diode will be discussed in the next lectures.